A very good morning, class 12th. The topic for today's class is halogens. We are talking about the P block of elements and we are talking about the group 17. The members for the group 17 are as follows: fluorine, chlorine, bromine, iodine and astatine. This astatine is radioactive, so we will not be studying it for any general chemical properties. Now, to learn the members, it's easier to do it via this shortcut where you can refer to them as full color brightness in atom. Since I am saying it's full color brightness in atom, full color brightness in atom, where astatine we will not be studying in detail. Talking about the electronic configuration now. Since they belong to the P block of elements, therefore the last electron will enter the P subshell. So the S subshell is fully filled and the P subshell of the last shell has got 5 electrons in it. Let's verify this. The atomic number for fluorine is equal to how much? 9. So 1s2, 2s2, 2p5. I hope that's clear now. Moving on to chlorine. The atomic number for chlorine is how much? 17. 1s2, 2s2, 2p6, 3s2 and 3p5, which is clear that your last subshell is the outermost P subshell with 5 electrons in it. For the others, you may not even know the atomic number, but you would know that in bromine this would be 4s2 and your 5 electrons will be in the 4p. For iodine, the 5 electrons would be in the 5p. For astatine, of course, we are not going to do it in details for the chemical properties. The 5 electrons are in the 6p. Fine. That's how you can write the electronic configuration. Now, as you go down, you can see the P subshell is changing from 2p to 3p to 4p to 5p to 6p. Now, since they have only one electron in the P subshell, their tendency would be to satisfy, that is, they have a tendency to gain one electron so that they achieve the inert gas configuration, that is the agenda. Since they have a tendency to accept an electron, therefore they generally form anions by accepting one electron, that is -1 is the common oxidation state for all the halogens. Since they accept electrons, therefore they themselves undergo reduction. By accepting the electron to become the noble gas configuration, since they undergo reduction, they act as very good oxidizing agent in general. Fine. Now, as far as their existence is concerned, all of them are found in a diatomic state. Because they have to share one electron, they exist as F2, Cl2, Br2 and I2. They exist as diatomic in nature and they have one covalent bond between them. Also, your iodine is found from extracted in the seaweeds. You should know this. There have been questions in entrances where they ask you how to obtain or where do you obtain iodine from. Also, there is an important ore of the halogens which is called as a carnallite. Carnallite is something that you should know. This carnallite is KCl, it's a double salt of KCl, magnesium chloride with 6H2O. There have been entrance questions on this particular ore, that this carnallite is an ore of halogens. You can extract chlorine from this and this is found from the dried up seas. Okay. Moving on to the first property, which is color. So, whenever we talk about color, the reasoning for color is always related to light because they have a tendency to absorb the light from visible region of spectrum, hence exciting the outermost electrons. This is generally the cause of the color for any identity. It is related to light, and they absorb light from the visible region, causes them to be colored. Now talking about the colors that are observed for these halogens are, this is a yellow colored gas, while this is a greenish gas. Br2 is brown red liquid. Iodine is a violet solid. So as far as the colors are concerned, the reasons are clear. Now we will move on to the physical state. Now as you can see, as I go from fluorine to chlorine to bromine to iodine, the physical state is changing from gas to liquid to solid, which means since the physical state is going from gaseous state to solid state, that means intermolecular force of attraction must be increasing. Tabhi to the molecules will move closer. So we have to talk about intermolecular force of attraction whenever we talk about the physical state. And the intermolecular force of attraction in these molecules, there is no electronegativity difference between the two F. As I go across from F2 to Cl2 to Br2 to I2, the size is increasing. So the intermolecular force of attraction has to be the London force of attraction, which is directly proportional to the size. Therefore, as I move from fluorine to chlorine to bromine to I2, the London force increases, therefore intermolecular force of attraction increases, therefore the physical state goes from gaseous to liquid to solid. This is a general fact whenever we talk about the physical state. Whenever there is a change in physical state, the answer is oriented around the intermolecular force of attraction. Also, if we talk about the melting points and the boiling points, this is also directly proportional to intermolecular force of attraction. Therefore, as I move from fluorine to chlorine to bromine to iodine, their melting points and boiling points will also increase, and the reason is due to the intermolecular force of attraction, which is nothing but your London force, because we are talking about the van der Waals force, because the weakest force, which is directly proportional to the size or the molecular mass. Fine. So the melting and the boiling points would also increase as you move from fluorine to iodine, as well as the physical state changes from gaseous to solid. Sorry for the delay. Now, the properties when we talk about size, ionization energy and electron gain enthalpy, then in that case, as you know, as we move down the group, the number of shells is increasing, therefore size would increase, also because the inner electrons prevent nuclear charge to reach the outer shells, which is called as your shielding effect. So as the shells are increasing, the inner electron protect the outermost shell from getting attracted by the nuclear charge. Hence, the size would always increase when we talk about down the group. Coming to ionization energy. What do we mean by an ionization energy? Ionization energy is when a neutral gaseous atom is transformed into a positive ion and there is a loss of electron. Now this requires energy, and this energy is your ionization energy. If you have doubts, please refer to class 11th video, periodic classification chapter number 3. Ionization energy is done in detail in my channel by Seema Makhijani. You can refer to that particular topic. So when we move down the group, as the size is increasing, your ionization energy is decreasing. It is inversely proportional to size because of the increasing number of shells. The outermost electron, this is your nucleus. These are the shells. as the electron moves away, its attraction by the nucleus is decreasing, so its removal becomes easier. Fine. Moving to the third property, which is electron gain enthalpy. When we talk about electron gain enthalpy, it is the tendency of a neutral isolated gaseous atom to accept an electron and become a monovalent gaseous anion, and there is energy released. Mind you, it is released. Therefore, the value is always negative for the halogens. The amount of energy released is the amount which is we are talking about. What is surprising fact is we expect that electron gain should be easier in fluorine because of its smaller size. Fluorine, chlorine, bromine and iodine. Out of these four, which should gain electron easily? Fluorine. So we expect this to have a more negative value, and so the electron gain should be easiest in this case. But there is an exception, which also we have done in class 11th. I'll just redo it, that delta H Eg is more negative for Cl than F, is an important question asked at many places. Fine. Okay. When we talk about electron gain enthalpy for fluorine and chlorine, you want this electron to enter into 2p5 or it can enter into a 3p5. We expect that the electron gain should have been more here, but surprisingly it is more here. The reason is these 5 electrons in this small compact 2p with 5 electrons causes electron-electron repulsion for the incoming electron. So this incoming electron faces a lot of repulsion from 2p5 as compared to a 3p5. The electron gain here becomes easier, as 3p is larger than 2p, therefore less electron-electron repulsion, therefore electron gain easier in chlorine than fluorine, and the key reason is these 5 electrons which cause repulsive interactions to the incoming electron. Moving on to the next important property is the reaction with water. When fluorine reacts with water, now fluorine is the best oxidizing agent to an extent that it oxidizes water, takes away the H, that is forms HF, and liberates oxygen, which clearly shows that you would have oxygen gas liberated if you immerse fluorine gas into water. Whereas what happens in case of chlorine? In case of chlorine, the chlorine is not that good an oxidizing agent. It does not oxidize water, it reacts with water. Now water has 2 ions, H positive and OH minus. One is taken by HCl and the other is your OH goes to Cl, so you get a HOCl. Now this is an unstable hypochlorous acid, and this acid being unstable, if you leave it for some time, you keep it for some time, this decomposes into HCl plus liberates oxygen. This is your single oxygen, also called as the nascent oxygen, which is the reason why it acts as a very good oxidizing agent, a good bleaching agent, is also because of good presence of nascent oxygen. Now when these two are mixed, chlorine being light green in color, this solution is yellow in color. But over a period of time, because the chlorine reacts with water to give you HCl and HOCl, so the color disappears. So this loses the color on keeping. Has been an important reasoning question, that why does chlorine water lose color on keeping, where you need to explain that chlorine water reacts to form HCl and nascent oxygen, or else why is it a good oxidizing agent? Why does it act as a permanent bleach? Now this question was also done in group 16 where I had compared the bleaching action of chlorine and SO2. Here it is a permanent bleach because it is by oxidation. It bleaches by oxidation, therefore it acts as a permanent bleach. Fine. Moving on further. Moving on to the next property, that is delta H dissociation, or also known as the bond dissociation energy of X2. Between two halogens you have a single covalent bond formed by PP overlap. So when we talk about F2, it is a 2p overlap. Cl2, it is a 3p overlap. Br2, it would be a 4p overlap because you have a NP5 and it has one electron less. So it overlaps with another NP5 to form a covalent bond by overlapping of orbitals. Here you have a 5p overlap. Now as the size increases, the overlap becomes ineffective. So what we expect is that in case of F2, the bond should be smaller. In Cl2, it should be larger. In Br2, it should be all the more larger. And in case of I2, it should be the largest when we talk about the bond length. So for bond length, we expect this is how it should be. And therefore, this bond should be easiest to break. Hence, we say this has the lowest bond dissociation energy, and that is correct because of the larger size and ineffective overlap of p orbitals. Makes the bond weak. Since this bond is weak, therefore the amount of energy required to dissociate it would be less. We expect that the bond dissociation energy should be the least is here and it is here. Now till this point it is okay. But when I say it should be maximum for fluorine, then the answer is not correct. The reason is, in case of fluorine, when these two fluorines form a bond, there are 6 electrons left, 3 lone pairs. Because of the small size, these lone pairs are close to each other and they cause a lone pair repulsion. And this lone pair repulsion leads the bond to become weaker. Hence, the strongest bond is not that of F2, and we have the order is not like this. There is a change in order. The order comes out to be, you have Cl2 has the highest bond dissociation energy, then you have Br2, then comes F2 due to your lone pair repulsion, and the least is I2. This has been an important question in the boards as well as entrance. You should know this order, that there is an exception for fluorine owing to its lone pair repulsion, which is actually present in all of them. But due to their larger sizes, this lone pair repulsion is very less. Because of fluorine's small size, there is a huge lone pair repulsion which makes the bond weaker. So the bond dissociation energy is maximum for chlorine and not for fluorine, is the important exception that you should know of, which is despite your 2p overlap, which is should be strong, but due to the lone pair repulsion, this bond becomes weaker. So the bond dissociation energy is lower. Moving on to the next property, which is the oxidation states for group 17 members. The electronic configuration generally is Ns2 Np5. Now since the electronic configuration is like this, the tendency would be that it can accept, all of them can accept an electron here. So general oxidation state therefore becomes -1 because they have a tendency to accept electrons. Now this is true when you are talking about ionic bonds where electrons are given, or bonds with metals where metals can give the electrons. But in case the bonding is with non-metals, that is when there are covalent bonds being formed, then what happens? Then there would be electron sharing. So if the electron sharing happens, then the oxidation state can also be +1 if it is with more electronegative atom. Beyond this, there can be unpairing of the p electron into d. If this happens, you would end up in this as configuration. You have 3 unpaired electrons, so the oxidation state will become 3. But this would only be possible if there is a presence of D subshell, which means this will not be possible for fluorine. Fluorine has no D subshell, so fluorine can only show one oxidation state, that is -1, because fluorine is the most electronegative atom. What is the electronegativity of fluorine? Fluorine has electronegativity of 4 on the Pauling scale, since it is the most electronegative. So for fluorine, the oxidation state is only 1 owing to absence of d orbitals and -1 owing to its highest electronegativity. We will note it down somewhere later. Coming to the next, we can also have the unpairing of the next electron, that is you would end up in this. Now there are 5 electrons unpaired, so you can have a +5 oxidation state. And lastly, this electron may also get unpaired and you would have 3 d orbitals occupied. That means you would have +7 as the oxidation state. So halogens are tending to show, the oxidation states of halogens are from -1, also +1, +3, +5 and +7. They show odd oxidation states owing to the odd electrons in the outermost shell, that is the p subshell. We have 5 electrons. On unpairing, it leads to these oxidation states. Also -1 for fluorine, it has absence of D, therefore +3, +5, +7 etc. would never be possible. Also fluorine is most electronegative, so nobody can take electrons from it, therefore the oxidation state is negative oxidation state of 1. That should be clearly understood. For the other halogens, you can have these oxidation states. Now the oxidation states like this are applicable to chlorine, bromine, iodine, while this is only applicable to fluorine, only shows a -1. Of course, this oxidation state can also be shown by chlorine, bromine, iodine, but +1, +3, +5 and +7 can never be shown by fluorine owing to the absence of d orbitals. Fine. Moving on to the anomalous properties of the first member, which is fluorine. It has the smallest size. Also in the periodic table towards right, as you move, the size becomes less. Since the size is small, its delta electron gain enthalpy is going to be high. Also, it will have the highest electronegativity, which is 4.0 on the Pauling scale, already known to us. Beyond this, it has a high delta Hi, that is electron removal is difficult from it. Also, it shows only one oxidation state, that too -1. Oxidation states, sorry, it should be oxidation state. The oxidation states of +1, +3, +5 and +7 are not for fluorine because of its absence of d orbitals and having the highest electronegativity. Beyond this, you also have FF bond dissociation energy is low owing to the lone pair repulsion. So these are the exceptional properties of fluorine. On top of it, it has tendencies to, it is the best oxidizing agent, hence can also oxidize water to O2 as already done. Fine. Let's compare the oxidizing agent property of chlorine and fluorine. Now we expect oxidizing agent property. The answer that we have is fluorine is a better oxidizing agent than chlorine, and the question is why, despite the fact that electron gain is faster in case of chlorine than in fluorine, as discussed in electron gain enthalpy. So talking about the 3 factors, the first step that you need is to dissociate it, because it has to be accepting electron in a monoatomic state. The first step mein we will dissociate the bond has to be broken down, that is enthalpy of dissociation and we know F2 bond is weaker, so the enthalpy of dissociation will be higher for chlorine because of the lone pair repulsion discussed already. Coming to the electron gain enthalpy, we very well know electron gain enthalpy is good for Cl as compared to F, that is, this has a more negative value, so electron gain should be better for chlorine. Moving on to the last is the hydration. Hydration enthalpy is directly proportional to charge, which is same for both, upon radius. So, since fluorine has a smaller radius, hydration will be more for fluorine than for chlorine. The net effect of all these three, it is found that there is a low DeltaH dissociation and a high DeltaH hydration. Now this energy is required, this is released, and this hydration is also released. So since there is a high hydration enthalpy, this leads to make F2 a better oxidizing agent, because all these reactions are bound to happen in water and they are applicable for single atom of halogen, not for the molecule. So F2 may say the first step is it will form an F, then it will gain an electron, and then this would happen in water. So the hydration energy released compensates for the lesser electron gain enthalpy. Hence, for fluorine you can say that the released hydration energy compensates for less negative electron gain enthalpy of fluorine, hence making fluorine the best oxidizing agent. With this I come to the end of this particular lecture, and in the part 2 of halogens I would be taking up the HX acids, that is the hydrohalic acids, and your oxo acids of halogens, plus some other properties which we are left with, like uses, etc. Fine. With this I close the class. I hope you are liking the videos, you are understanding the concept of chemistry involved in the chapter of P block group 17. Please do keep liking and subscribing. Thanks a ton. Bless you loads. Do well in life. Bye.